Hi there and welcome. This is a live feed for GCSE and this is going to be some OCR Gateway Foundation GCSE papers. Now that if you're on the higher tier, then I suggest you stick around because these will still be good practice for you. Just turn the sound on. Apologies, that were a little bit of a false start there. Okay, so this is an OCR Gateway GCSE stream, and if you're on the higher tier, then I suggest you stick around because it'll still be good practice for you going through a whole bunch of things, a whole bunch of content for your topic. If you're A-level, then you needed to be watching the one that I did a little while ago, so skip back. Don't watch this one, watch that, and there's loads of streams that I did for your paper tomorrow available for you as well. So I'm just going to jump straight into the videos in just a second. Just remember though, this is your last paper, okay, for science, and you're ready for it. Okay, relax, go in there, do your best, focus on, showing your qualities. You can do this. Okay, so be really positive there. This is the last little push. When I go through the questions, focus on understanding how I solve the problem. Don't just learn the answers that I put down. Use the way that I solve the problems to solve the problems in your exams tomorrow. Okay, let's jump into the visualizer and let's get on with the paper then. Okay, so hopefully you can see that all right. Let me know that this is coming off okay. Turn off the bangers. I will have a little look through the chat later on if there is anything, so do let me know if you've got questions. Okay, so let's just jump straight in. It's going to start with some multiple choice. Multiple choice is not necessarily easy. Okay, so think before you answer. Don't just jump to your first conclusion. Okay, which shows the amplitude of the wave. Amplitude is from the equilibrium position to the height of the wave, so the answer is A. Which energy source is non-renewable? Non-renewable means it will run out or it doesn't come back as quickly as we can use it. So the only one that doesn't come back as quickly as we can use it is coal, which formed over millions of years. So the answer is B. Make sure you know your renewables from your non-renewables before you go into that paper. Which of these is not true of all electromagnetic waves? Now, a lot of people, when they answer these, they don't pay attention to this and they go for the true ones. Okay, which is not true? Well, they are all transverse waves, that's true. They have the same wavelength, no, that's not true. Okay, they vary in wavelength and frequency. They can all travel through a vacuum, that is true, and they all travel at 300 million meters per second, so your answer is B. They all have the same wavelength. Which correctly describes electricity supplied to homes in the UK? It's 50 Hertz alternating current. So you can see how these seem pretty reasonable. It's 230 volts, not 230 Hertz. So AC means going positive and negative 50 times per second, so the answer is A. An egg strapped to a trolley can be used to demonstrate a car crash into a wall. So this is about crumple zones secretly, which would cause the least amount of damage to the egg. Well, let's have a little think about the least amount of damage. So if there was no spring, that would cause more damage. It's not going to be that. If there was no strapping, that would cause more damage. That's like a seatbelt, basically. A larger egg, well, that wouldn't necessarily change the damage at all. A smaller deceleration. So what they're going for with any car safety feature is that they decrease the acceleration or they decrease the deceleration. So it means that because Newton's second law states that the force is equal to mass times acceleration, lower acceleration, lower force, and deceleration is just a negative acceleration. Okay, the bar chart shows the electricity generated from different sources from 2005 to 2010. This one's quite a tricky one, I think, actually, so you've got to be really, really clear on it. Which statement is correct about the information in the bar chart? Each year more electricity is generated by hydroelectric than wind. So hydroelectric is the bottom one, wind is the black one. So actually that is true. And we're going to check through the rest, even though the answer is A, because you need to have that skill, okay? The other ones are distractors, so they are there to kind of put you off a little bit, but you can do this, okay? The amount of electricity generated by hydroelectricity is constant. Well, no, that's not the case. It does change. The electricity generated by wind has increased every year from 2005 to 2010. No, it didn't always increase. This was about the same, maybe even slightly less. So that was a tricky one there. That's not true. The total electricity generated has increased to 19,000 gigawatt hours. Now actually, if you read this off the scale, it comes out at 19,500. So that seems very true, but is not. You see how they're written to seem like they might be true, to be close to being true. Okay, so which graph shows an alternating current? Alternating current means it varies from positive to negative. Okay, so this one is always positive. This one is always positive, even though it does go up and down. This one goes up and down, but it's always positive, and this one goes from positive part of the graph to the negative part. So the answer is D here. Okay, it's this one. All radioactive sources have a half-life. Which statement about the half-life of the sources is correct? The half-life is the time taken for the radioactive source to become safe. No, not quite. It is a time. Is the time taken for half an atom to decay? No, not quite. Okay, because there are loads and loads of atoms in any sample. The half-life is the time it takes for the activity of the source to decrease to 0. No, absolutely not. It's about it changing by half. It's the time taken for the activity to decrease by half. And we'll say something about half-life. Loads of people have been misunderstanding that in these GCSEs. It is not the case that at one half-life the activity halves and then at the same time the next half decreases. It's in the half-life it keeps decreasing by half each time. So make sure you pay attention to that. Okay, this is one where you needed to memorise the equation. Actually, even though it's a multiple choice, really there's a bit of thinking to do here. So this is the equation. Gravitational potential energy is mgh, mass times gravitational field strength times height. There's a clue to that because they've told you about g there as well. You've got a mass and you've got to convert that into kilograms before you do anything. And you've got a distance, you've got a height, and it is already in meters, so that's okay. So you want kilograms and you want meters, okay? So you don't convert out of those units. Convert to kilograms, leave it as meters. So mass 0.4 times 10 times 0.8 comes out in the calculator as 3.2. Always do things in the calculator. Make sure you take one into that exam with you. So the answer is B, 3.2 joules. The national grid transfers energy efficiently using high voltages. Why are high voltages more efficient? Okay, well this is because increasing the voltage actually decreases the current, which heats the wires less. So there's quite a lot of thinking you have to do about this, okay? And the difficulty with this is that actually voltage is proportional to current. So normally if you increase voltage, then you increase the current. But because we use transformers, and the power is the same on either side of the transformer, then increasing the voltage from one side to the other decreases the current on the second side. Okay, so make sure that you're clear on that. It's all about this. Basically, you have less current, so you have less heat loss. That's the key kind of principle in that little section there. Okay, so this is about electromagnetic spectrum. Okay, it's about microwaves particularly. The wavelength of microwaves can be measured using chocolate. The turntable is taken out of the microwave and the chocolate is put in the microwave. The chocolate is left on full power for 10 seconds. So you basically get these two soft spots. The soft spots are half a wavelength apart. So the microwave only cooks the chocolate at the certain points, at the kind of peaks of the wave, if you like, and the troughs of the wave. So you have to first of all use the picture to measure the difference between the two soft spots. You don't have to get your ruler out, you use the ruler here. And you can see you want to go from centre to centre. So the thing they're asking you to do is use the picture to measure the distance between them. So this centre to this centre here is a distance of 41 millimetres. Now that's pretty tricky to get accurate because it's pretty tricky to see the centre there. What I suggest you do is you actually look at the two kind of ends of the little circle they've given you and use that to work out the middle of that circle, the centre of that circle. And then they've asked you a full wavelength is double the distance between the two soft spots. So what is the wavelength in the microwave in millimetres and in metres? So you have to get both of these to get the single mark. But notice how they've told you to double it. Okay, now if you didn't double that, you didn't read that too carefully. So make sure that you do double for the wavelength. 82 millimetres is the wavelength. Now converting that into meters, you have to divide by 1,000. Milli means 1,000. So make sure that you can do that fluently, converting your units. This time, although this is one that you have to remember, they give it to you because they're not testing your recall like they were in the previous question. Okay, so you use the formula wave speed is frequency times wavelength. Now the frequency is given here and it's a big long number. Okay, so you can just type all that into the calculator, but here I'm suggesting you be really careful and count off your zeros into the calculator and count off your zeros out of the calculator. Or you can use standard form, and I'll just do that briefly at the end. Now you needed to remember, and the reason why they gave you that first part of that question is you use a wavelength in meters, not in millimeters. So you needed to use the right one from that previous question. Okay, and then you type all that into the calculator, and look what I've done. I've accidentally written down one more zero, but because I've taken the time to count the zeros off the calculator, I'm not going to lose that mark. So there's a mark for simply substituting the correct numbers into the equation. So make sure that you get that first mark. And there's a mark here for the actual final answer, which is 200,900,000. Well, you need to say it, you just need to make sure the zeros are right. Okay, the picture shows a radiator in a room of a house, and the radiator is full of water. They've told you this information here. The water enters the radiator at a higher temperature than when it leaves. Suggest why this happens. So this is about energy transfers, right? So they're just looking for you to know that the water in the radiator is hotter than the surroundings. So the heat is lost to the surroundings. So energy transfers from radiator to surroundings. And then we always want you to talk about energy stores. So in this case, we're talking about a thermal store. The thermal energy of the store decreases. Okay, so less thermal store of energy in the water, so therefore a lower temperature. They've told you that the water enters the radiator at a higher temperature than when it leaves. So basically the question is, so you suggesting why is going to have a lower temperature at the end, and that's because of those thermal energy stores. Okay, this time they're asking you to calculate the amount of energy given to the room by 1.5 kilograms of water as it passes through the radiator, and they're giving you some other data. They've told you a temperature change, 3 degrees Celsius, so it came in 3 degrees hotter than it left. Okay, and they've told you the mass, and they've told you the specific heat capacity. So you need to remember an equation which links mass, specific heat capacity, and temperature change to the energy transferred. They've asked you to calculate the amount of energy. Look, that equation is energy is mass times specific heat capacity times temperature change. So the mass was 1.5, and you want kilograms, you don't convert out of kilograms. The specific heat capacity is this, 4,200, and the temperature change, delta T, is 3. So 18,900 is what the calculator comes out. Now in this case, they've given you a little box for the unit, and they've told you to show your working and write down the unit. That means there's a mark for memorizing the equation, getting the correct equation from your brain. There's a mark for the correct answer, and there's a mark for the unit. So even if you couldn't do any of this, just make sure that you know, you can recognize, oh, they've asked me to work out energy, and I know joules is the unit of energy, so I can pick up that mark there. The radiator has air trapped in it. The specific heat capacity of water, I've told you again. The specific heat capacity of air is a third of water. Calculate the specific heat capacity of air. So this is a very simple question. Actually, it's just a maths question. They've told you a number, and they've asked you to work out a third of it. So just calculating that, 4,200 divided by 3 gives you 1,400. The picture shows the radiators in the house connected by pipes to the boiler. This is the boiler, here's the pipes, and here's the radiator. Why are the pipes covered in foam? So this is just worth 1 mark. And they're looking for foam acts as an insulator, so reduces heat loss. Now what I would really want you to say actually is foam has a low thermal conductivity. I think that is the type of answer we're after. So maybe upgrade your response from insulator to having a low thermal conductivity. It means that heat doesn't conduct well through the foam. Okay, so Molly, here's Molly, this question is about Molly apparently, pulls toy cars along a floor in a laboratory. She measures the force and distance moved each time. Her results are shown in the table below. Which 2 cars took the same amount of work to pull? Okay, so here you need to memorize the equation for work done. Work done is force times distance. And then basically you're just asked which 2 took the same amount of work to pull. So here I've just written out all the different equations. Look, force times distance. The work done for A is 10 times 2, 20 joules. Work done for B, 5 times 6, 30 joules. Work done for C, 4 times 5, 20 joules. And work done for D, 2 times 7, 14 joules. So which 2 took the same as A, and that's C. Okay, in another experiment to look at work done, Molly uses different electric motors to lift a large mass to find out which motor is the most efficient. She measures input and output electrical energy to calculate the work done on the mass. Here's her results. So this is not got to the question yet. Okay, so here we are, write down the question. Then there's Molly's statements. I think motor Q wastes half as much energy as motor R. So Q is the most efficient. Use the data and calculations to explain why Molly's statement is only partly correct and partly wrong. So you have to take your time to digest this and make sure you get to that question and you can use all this different information. So take your time, don't panic, don't think, oh, I don't know. The answers are all here. Okay, so there's two parts to this. So firstly, Q wastes 40 joules and R wastes 80 joules. Now where did I get the waste from? See, I've done a second little column here. They've input this amount of energy and they've output this amount of energy. So take the input and deduct the output energy, gives you 40 joules waste. Similarly with R, 2000 joules input, 1920 gives you 80 joules waste. So efficiency, so basically she's partly correct here. Motor Q wastes half as much as R. So this bit is correct. So we've made a statement to say that, yep, 40 is equal to half of 80. We've got the mark. And then R is more efficient, so the second statement is incorrect, right? So the next part, this part, she said, so Q is the most efficient. But the efficiency is not how much energy is wasted, it's the percentage of energy that's used usefully. So you need to remember the equation, efficiency is useful over total. It could be useful energy, it could be useful power. But essentially, the output energy, that's the useful, and the input energy, that's the total. Okay, so 760 divided by 800 is 0.95 or 95%. And the efficiency of R, 1920 over 2000 is 0.96, so 96%. So actually the second statement is wrong because in fact R is more efficient by 1%. So calculate the difference between the input and the output for motor R. It takes 20 seconds to lift the mass. Calculate the difference in input and output power. So you have to remember the equation for power. Power is energy transferred over time, or power is the rate of transfer of energy. So here you have to look at the inputs for both, just for R rather. So motor R is all we're interested in this time. So you needed to go back to this data that you're given, look at the input energy just for R and the output energy just for R, sorry. And you need to calculate the power input for R and the output power for R. So if energy transferred over time, you're told it's 20 seconds, so the input is 2000 over 20, the output is 1920 over 20, and this gives you 100 watts, and the output gives you 96. So the difference is just 100 take away 96, so it's 4 watts. And there's a lot of thinking to go into that. Okay, so again, you must take your time, digest exactly what it's asking you to do. Don't just put down your first idea. Okay, really think about this. Memorizing that was a mark. So if you just remembered the equation for power, you get 1 out of 3 marks, which will be enough for a decent grade. Okay, and then inputting the numbers in and calculating 100 and 96 will be the second mark, and then finally for the answer, the third mark. So the stopping distance of a car is important for road safety. One factor that affects stopping distance is reaction time. The picture shows student A using a rule drop test to measure the reaction time of student B. So here's student A going to drop it, student B is going to catch it. Use the picture to describe how this method measures reaction time. We're not looking for a lot of detail this time, we're just looking for a description. You drop the ruler randomly and you measure the distance the ruler drops during this time before it's caught. So basically, person A drops it, they haven't actually told you that. Notice, so that is the answer to this one. If the things they haven't told you can be the answer to a simple describe question. Then you calculate reaction time from the distance the ruler fell. Okay, is the second mark. So it's quite simple actually, that one. It's just really, did you understand this diagram here, this picture they've drawn you? Write a method to compare the reaction time of boys and girls. In your method, describe how you make the measurements accurate. So you see how this is 4 marks, and really it's like two 2-mark questions. So first of all, you need to say something about how you compare boys and girls. So you'd use the drop ruler test for a group of boys and a group of girls. Then they're looking to see some control variables. So you use girls and boys of the same age, maybe. Maybe you use the same hand, so you use their dominant hand, maybe. Okay, and you just need 2 of these. So you could have said no practice beforehand, you could have said same time of day, and you could have said no distractions. And then lastly, something about how to make a more accurate look. You can eliminate anomalies and calculate a mean. Will give you more accuracy because you'll have random uncertainty in this. Okay, another factor that affects stopping distance is braking distance. A graph below shows how the braking distance for tyres with different tread depths on concrete. So whenever you get a graph, look carefully at the axes. So this axis says tread depth. So these are the deeper treads, okay? It means that the tyres are less worn, basically. They've got deep treads on them. Whereas these, down the bottom here, they have been worn, so their treads are less deep. And this is the braking distance, so this is how far it goes before it comes to a stop, once the brakes are applied. What trend does the graph show? Well, look, the line is generally sloping downwards, so lower tread depth, higher braking distance. So just get that simple description of the trend the graph shows. It's worth a mark. It's as tread depth decreases, braking distance increases. Use the data from the graph to calculate the difference in the braking distance between a tread depth of 2 millimeters and 5 millimeters. So what you can see, and you can maybe just see my lines that I've drawn there, with a ruler really carefully, I've found 5 millimeters, found 2 millimeters, along the grid lines to the line of best fit and down to the axes. And I've read off carefully from the scale 32 millimeters here, 43 meters here, and the difference between them, 43 take away 32, gives me 11 meters. There's 3 marks for that. One's for showing the interpolation skill, one's for showing that you understand how to do the difference, and the last one is for 11 meters. Now, I'll just say about graphs, we're expecting you to use graphs to half a scale division, half a small square accuracy. So double check that. Make sure you're going into that exam paper with a sharp pencil so that you can actually use the graphs to that level of precision. Next one here, a car has mass 2 tons and they've told you the conversion from tons into kilograms. So you can straight away say the mass is 2,000 kilograms. They've told you 1 ton is 1,000 kilograms. And decelerates at 2.8 meters per second squared. Calculate the force being applied to the brakes. Here's the formula. Again, they've given you the formula. Notice it's only worth 2 marks now. So there's a mark for putting the numbers in the right place, having converted the mass, and a mark for your final answer of 5,600 newtons. Again, use a calculator so that you don't have to think anymore, so that the calculator makes fewer mistakes than we do with our brains. Okay, so that was quite a simple one. Make sure that if you're given the equation, you can show how to use it. Student made some notes on a simple model of the atom. The atom consists of negatively charged nucleus surrounded by protons. Are we seeing something here? Most of the atom is just empty space. Yeah, okay, fair enough. The nucleus contains neutrons and ions. Does that sound really that sensible from what you've learnt? Okay, the student has made 3 mistakes. Write down the 3 mistakes the student has made. Right, okay, so 2 of them I think are really obvious, 1 not so much. Atoms have a positively charged nucleus, right? Individual atoms have positively charged nuclei. Okay, so that was a mistake. Most of the atom is empty space. Yes, that is true, but it is inhabited by these electrons in their energy shell. So they haven't mentioned the electrons. Okay, there are electrons in energy shells. Okay, I'll just put the electrons there. The nucleus does not contain ions. It contains neutrons and protons. Okay, that's what I've said there. So you could actually do that by correcting those statements there, and I'm sure we would mark the whole thing and you would get those marks if you did that correctly. So this is quite a simple one really. You just have to read, make sure that you know, and you can apply your knowledge to solving that problem. Some nuclei are radioactive because they are unstable. The nucleus atom could be shown as, well, X is the kind of code from the periodic table, A is the mass number, okay, that is the protons and neutrons, and Z is the proton number, the atomic number. Okay, so what is meant by A? That is the atomic mass number, or you could have said the protons plus neutrons. Okay, so the top one, and it will always be the larger of the two because it contains both protons and neutrons, okay, is the mass number. And here's an equation. Describe what is shown in this equation. So all you have to really say in this one is that carbon-14 is decaying into nitrogen-14. Okay, so describing carbon-14 decaying into nitrogen-14, and it's decaying by beta emission. They didn't want any more detail on this. What is actually going on is that a neutron is turning into a proton and it's giving out the beta particle. So you might want to give the more information than they've given you, but in this one it was just looking for a simple description that you can see carbon decaying into nitrogen plus a beta particle. You can use E minus or you can use the beta particle here. Essentially these questions are pretty straightforward because all you need to do is make sure the top line balances and bottom line balances. They haven't asked you to do that this time, they haven't asked you to solve it, they've just asked you to describe what's going on. So these cotton bud walls have been treated with gamma rays. Why might they do that? Cotton wool buds have been irradiated but not contaminated. This is the difference between two risks involved with radiation, irradiation and contamination. Now irradiation is a lower risk than contamination because irradiation is temporary. So let's have a look at the answer I've given. Irradiation is being hit by a neutral particle, e.g. the alpha, beta or gamma. So basically irradiation is having some radioactive particles hit you or hit a thing. Contamination is when a radioactive material leaks or gets onto a surface. Okay, so that's what we're more worried about because that is a longer term risk. Contamination causes a long-term radioactive hazard, whereas irradiation is temporary, so you could say either of those two things. And lastly, you need to have the point that contamination is a higher risk than irradiation is. Now here's the 6 marker. A lot of you will be thinking carefully about your 6 marker. So when you do a 6 marker, be careful to plan the question, plan your answer really carefully. So here's a whole lot of stuff about the information. Okay, 2 circuits to investigate the difference transformers make to circuits. Here's our first one. We've got a 12 volt AC supply, transformer to step it up, transformer to step it down. Here's the second circuit. We've got no transformers at all. They're both going through the same resistance wires, you can see. So firstly, compare the 2 circuits, including reasons why the transformers make a difference. So actually, you can see I'll put a little 1 because this is going to be my first paragraph. Then 2, suggest how circuit 1 could be improved to make the bulb glow more brightly. A lot of people, they just do this because they tend to do the last thing that the question asked them to do. So many people are going to start this, well, we could do something to change this to make the bulb glow more brightly, but the smart ones are going to think, that's my first paragraph, that's my second one. So this is what I mean by planning with the question. So circuit 1 has transformers which raise the voltage across the resistance wire and lowers the current. So this is the job of a step-up transformer. It increases the voltage, but it lowers the current. This means energy is wasted, less energy is wasted in the wires due to the heating effect of currents. That's come back again as a really important idea in the P7 topic, P8 topic. It's P6 actually in Combined Science, isn't it? Global physics, whatever they call it. Basically, currents cause heating. If we limit the current by using a step-up transformer, we have a less of a heating effect, so we waste less energy. Okay, the step-down transformer increases the current and decreases the voltage, so the bulb doesn't blow. I should have put blow, I put glow. So that's the job of reading through your answer. So basically this one then brings the voltage, sorry I've done that wrong, brings the voltage back down and increases the current. And this means that you've just got 12 volts across here, not any higher voltage than that, so the bulb doesn't break. So this means the bulb glows more brightly because the whole system is more efficient than circuit 2. So circuit 2 doesn't have these transformers, and I've finished my comparison of the 2 circuits. Second paragraph suggests how circuit 1 could be improved, so it's still not good enough for them. They want is this bulb even brighter. So how are we going to make this bulb even brighter? We could reduce the length of the resistance wires because they're looking for you and knowing that a longer wire has a higher resistance. So that's the first thing we could have said. We could reduce the resistivity of the wire, so different materials have a lower resistivity, they have lower resistances. We could also increase the thickness of it. Okay, so thicker wires have less resistance than thinner ones. Lastly, you could also increase the ratio of turns from primary to secondary on the step-up transformer, meaning the current is even lower, meaning even less energy is wasted. And similarly, you could do the same here and have a lower ratio from primary to secondary. Last one now then, the washing machines have an outer casing made of metal. The picture below shows an earth wire. So we should be thinking that we're going to get our standard explanation of how an earth wire works here into this question. The live wire becomes loose and touches the outer casing. You see this? So earth wires are a safety feature of our plugs for whenever we have a metal encased appliance. Explain why this does not give you an electric shock. So we need to explain this. Right, this is your standard 3 marks for how an earth wire and a fuse work to keep you safe. So learn this, put this down if you see anything about a fuse wire and an earth wire. The casing is earthed, which means a path of very low resistance. So we're just looking first statement, earthing is low resistance path. This means charge flows to earth rather than the user. So when there's a surge of current that causes the fuse to melt, or you could say to blow. Right, now the fuse melts, breaks the circuit, and rather than flow through the user, the high current flows down through the low resistance path and the user is safe. So there's our 3 marks there. Earth is a path of low resistance. Charge flows to earth rather than the user when a surge of current causes the fuse to melt and the circuit to break. I might just put that in there as well because it's a good one to remember. Last one, the earth wire is thicker than the live wire and neutral wire. So this is this idea, thicker wires have a lower resistance. Suggest why the earth wire is thicker. Thicker wires have lower resistances. Right everybody, I hope that was useful to you. I'm not going to look at the chat because the chat has a lot of A-level students who are here because they've got an exam tomorrow, and I don't want to draw attention to their silliness that they've been doing. But all the best for your paper on Friday. I'll be back in just a little while with some higher tier questions and also some separate science physics questions for your paper on Friday. If you're an AQA student, then I'll be back in to do some AQA questions tomorrow evening as well. Okay, so thanks a lot for watching.